Alright, so in this video I'm going to be explaining this important paper with the title Efficient Representation Learning Using Random Walks for Dynamic Graphs. This paper in 2019 from from Sydney. An important part of machine learning on graph is vertex representation learning. For example, learning a low-dimensional vector representation for each vertex in graph. Recently, several powerful techniques for unsupervised learning have been demonstrated to give state-of-the-art performance in downstream tasks such as vertex classification and edge prediction. These techniques rely on random walk performed on the graph in order to capture its structural properties. These structural properties are then encoded in vector representation space. However, most contemporary representation learning methods only apply to static graphs. Nowadays, because of the advances in dynamic graphs, like problems in temporal graphs, like diffusion-based graph generation, so we have a sequence of graphs at each instance of time, or at each iteration of the denoising process of diffusion. So we need to understand how we can leverage structural information for dynamic graphs. We propose computational efficient algorithm for vertex representation learning that extend random walk-based methods to dynamic graphs, such as the temporal graph or spatiotemporal graphs. So we want to see if we can use against techniques like skipgram that we used in static graph for structural representation for dynamic graph. Given a corpus of target context pairs, the vertex representations are found by learning a vector representation for each vertex that then combined by a specific function approximates the probability of co-occurrence of the target and context vertices in the vertex pair corpus. So in particular, skipgram models the conditional probability of this vertex pair by a log linear function. And the vertex representation Z for all vertices can be found by minimizing the cross-entropy loss. But a dynamic graph is a series of undirected graphs. Now, when updating random walks on graphs, we consider a set of vertices which have changed directly as a result of additions and deletions of vertices and edges. Specifically, we denote the set of vertices containing no added edges as this added edges, and these deleted or removed edges. So, to analyze the effect of graph changes on the random walks, we define affected vertices and affected walks. All vertices that are the set of vertices contain the set of added edges and the set of removed edges. The affected walks are all random walks from the corpus of random walks that contain at least one affected walks. So this is a multi-class classification on Cora dataset for different walk length and number of walks. And this is an example of graph G1, graph G2 as an added vertex D. Now we add this vertex B and this edge BD. So our goal is to update random walk corpus so that it is indistinguishable from random walks generated on the updated graph. The input data for a static algorithm is a snapshot of graph and the random walk parameters. So to motivate an algorithm that allows us to update to our random walk corpus, we return to the definition of affected vertices and affected walks. So in static graph, we can create, once you have a graph at time t+1, for example, you can create a random walk for that. And this is a naive update. If you update, and this is the unbiased update. So we propose to use this information in training the skip-gram model. The incremental algorithm starts with the vertex representation from previous graph snapshots and introduces randomly initialized vectors for the new vertices.